Hello guys, I'm here again. My name is Joseph AGK RG. This past few weeks has been a very busy week for me. But anyway, I'm back here with you again. Today, I'm going to show you how to work with binomial distributions. Basically, how to calculate binomial probabilities. And also, their applications. Now, you recall that my previous lecture, we are talking about discrete probability distributions. And I explained that a probability distribution simply means a selection of random variables, the values that those random variables can take, and their corresponding probabilities. Now, and I give you the examples that we'll discuss in this class, in this lecture series, the binomial, the Poisson, and the hypergeometric. Today we'll be dealing with binomial. So in fact, this week and the following weeks, we'll be working on binomial. After that, we can now go to Poisson. Okay. By the time I begin, I want to give, I believe in giving credit to whom credit is due. When it comes to binomial distribution, it was the Swedish mathematician Jacob Bernoulli that developed this binomial formula. And because of that, sometimes we call it the Bernoulli distribution. Okay, and this is Bernoulli right here. Okay, let's begin. Now, we start with binomial experiments. Many probability problems have two outcomes, or they have an outcome or that are two. Let me put it in a different form. Many probability problems have two outcomes, or outcomes that can be reduced to two. Let me give you an example. A coin. When you toss a coin, the outcome is two. Either it's a head or it's a tail. How about this? Basketball game. In a basketball game, either the winner, a team win, or the team loses. How about blood pressure? Either it is normal or it is not normal. For example, the doctor might check your blood pressure and say, oh, it is so and so amount, 180/50, 100, whatever they call it. The bottom line is that either it is normal or it is not normal, which is also two outcomes. In a multiple choice question, for example, you might have 5 options. Option A, B, C, D, and E. So you choose answer from these 5 options. But the bottom line is that the answer is either correct or it is not correct. See, so it always leads to two outcomes. So this kind of scenario, we call it the binomial experiment. And that is how binomial distribution came about. So the definition is here, that a binomial experiment is a probability experiment that satisfies this requirement. There have to be fixed number of trials, which we give we represent with n. Now, each trial has only 2 outcomes, which I have explained in my previous slide. Now, these 2 outcomes, we call it a success or a failure. Now, a success doesn't mean that it will be on the positive side. It depends on what you are looking for X. For example, if you're looking for the team, the probability that the team loses, in that case, your success would be the probability of those that loses. So it doesn't have to be on positive side per se. Now, the probability of events or of the success will represent it with P, and it remains constant. See, it remains constant. Now, the probability of failure is, we call it Q. It's always 1 minus P that will give us the Q. I will explain that in a few minutes. Remember, like I said at the beginning of this lecture series, I'm gonna make it very simple for you. Now, each trial is independent also. So that this team wins does not have nothing to do with the other team winning. These are independent. So which leads us to the binomial distribution. So the binomial experiment, okay, and their corresponding probability of the outcomes. That experiment, that binomial experiment, and the probability of its outcome, that's what we call binomial distribution, basically. And we use this formula to calculate it. Px equals n combination x times p to the power x times q to the power n minus x. I don't worry about the formula, the appearance, how it looks. It looks like a monster, but it's not. When we start using it, you will discover that it's actually simple. If you look at this side, ncx, we did it when we were doing the counting rules. We did combination. It means n combination x. So, and I showed you how you can get it with a calculator. And I'm going to show you again today. P is the probability of success that I just explained. Q is that of failure. And you get Q by just doing P minus 1 minus P. So let us apply this rule in solving some problems, okay? Hope you enjoy it so far. All right, look at this. It says 40% of all voters support proposition A. Well, there are some places that they use this kind of, law, call it proposition A. Like some state like California, they have so many proposition this, proposition that. Proposition simply means, I think it comes from some kind of referendum. Okay. Anyway, so 40% of all voters support proposition A. If a random sample of 10 voters is polled, what is the probability that exactly 5 of them support proposition A? All right, let us go by step by step. How many percent support it? It's 40%, so our P is 0.4. 0.4 is the same as 40%, which means that Q is 1 minus P, which is 1 minus 0.4, it gives us 0.6. Now it says if a random sample of 10 voters, so N is 10 because sample of size is 10 people we have selected. So you say what is the probability that exactly 5, that means our X is 5. So now this is how you get the numbers. Next thing is to plug them into this formula right here. Okay, so that means that anywhere you see N in this formula, anywhere you see N in this formula, see, you put 10. Anywhere you see X, put 5. Anywhere you see P, put 0.4. Anywhere you see Q, put 0.6. And that will give us this. Px is 10 combination 5 times 0.4 raised to the power 5 times 0.6 raised to the power 10 minus 5. 10 minus 5, why? Because it says n minus x here, okay? Now, so like I said, when we are doing a counting rule in one of my previous lectures, I showed you how to get this part right here with the calculator. N combination x. Start the calculator. Press n is 10 is there, and say 10. See where you have a PRB, which means probability. Press it, and this is NCR. That is the 10C5. So go right there, and then press the enter key. Okay. Then put 5. Then press the equal sign. You get the answer right away. See? Now, times this, 0.4 to the power 5. So, 0.4 raised to the power 0.4 raised, see, this is the key for raised to the power right here, 5, okay, equals 0.0102, you can see right there, times, then this one is 0.6, 10 minus 5 is 5, so this means 0.6 to the power 5, because 10 minus 5 is 5, so 0.6, or if you like, you can get it right away, raised to the power 5, 0.0776, you can see right there. So that you multiply them, you're going to have 252 times, okay, 0.01, 0.01024, okay, times 0.07776. Give me 0.20065. If you round it up, you get 0.201, which is what I got here, which is 20.1%. So, which means that if you select if you select 10 voters, 20.1% of them exactly sorry, my mistake. The probability that exactly 5 of them will support the proposition A is 20.1%, or 0.201. Now, I want to show you something very, very important. Now, instead of going through all these steps, you can get your answer from here. Once you have this part, your professor will know that you have shown your work, or that you have shown your work. You don't need to go through all this. So once you got this part, get it from the calculator right away. Watch me. You have 10 combination 5, you have 10, so you have 10, go to PRB, okay, right here, go to combination symbol, 5, equal, give me 252, then it's okay, times 0.4 to the power 5, put it in parentheses, okay, 0.4, okay, raised to the power, here, right here, 5, close the parentheses, times this one, 0.6 to the power 10 minus 5, so we have 0.6 raised to the power right here, 10 minus 5 is 5, okay, so put 5, close it, and that gives you the answer right away, 0.20065, so which round up to 0.201. So see, this one is easier, and because of that, we'll be using that method in other problems in this lecture. Okay, I'm sure you're having fun by now. See, it's very easy. So now let's look at some examples, more examples. I believe that solving more examples, the more examples you do, the more better you get at solving a particular problem. Or let me put it this way, the more examples you solve, the more good you get with statistics. Okay, look at this one. It says, find the probability that in 5 tosses of a fair dice, a 3 appears at no time, B, once, C, twice, D, 3 times, E, 4 times. A 3 appears. You know, this is a dice right here. Well, I think I have it somewhere. Okay. Let's see a dice right there. Now I can see that you have 3, 5, 6. You have 1, 2, 3, 4, 5, 6 sides. So this one dice will toss 5 times, so that our n is 5. Okay. Now, because a dice has 6 sides, the probability of success is 1 out of 6. The chance that 3 appears is 1 out of 6, which is our probability of success. So 1 out of 6, if you get it on a calculator, I usually have to instead of using fractions, I usually use decimal, because using fractions make it more complicated. So change this to decimal by doing 1 divided by 6. That'll give me 0.16666, which is 0.167. Okay? And I told you that to get Q, simply do 1 minus P, which means 1 minus P, which is 0.167, 0.833. See? So why P? How do I know that P is 1 over 6? Because a dice has 6 sides. So for a dice only, P is 1 out of 6 chances for 3 to occur. So now let's go back to the question. It says 3 occurs. Part A said at no time. At no time, that means our x is 0. See? Now we can plug all this thing into the formula. Whenever you see n, put 5. Whenever you see x, put 0. Whenever you see p, put 0.167. If you see q, put 0.833. We put them in this formula right here. And that will give us the answer to part A. So we have probability of 0 becomes, like I explained, we're just going to get it from here. 5 combination 0. 5, you go to PRB, combination 0, give me 1, times, in parentheses, 0.167 raised to the power 0. Actually, by law of exponents, a real number raised to the power 0 is, 1. So, but in any case, let me just put this in the calculator. 0.167, 7 raised to the power 0. Close it. Then times 0.833 raised to the power 5 minus 0 is 5. Okay, 5. Close it. That'll give me 0.401. You can see right there, 0.401. So the probability that 3 appeared at no time is 0.401, or 40.1% chance that it doesn't appear. Okay. Now, part B says once, that appeared once. That means our x. Remember, one of the properties of the binomial experiment is that P stay the same and Q stay the same and N stay the same. So when it says once, we say 1. That means the only thing that change is the x. So in that case, x is 1. So every other thing stay the same. So that the probability that it appeared only once becomes 5 combination 1. Press 5 here. PRB combination 1. Okay. Press 1 here. Equal, give me 5 times, okay, 0.167 raised to the power, okay, raised to the power 1. We know that it will be the same anyway, but I just put it to show you how to put it on the calculator. Times, okay, 0.833 raised to the power, okay, 5 minus 1 is 4. That gave me the answer right away. 0.402 again, 0.402. See? Okay? This is just a coincidence. It is a coincidence that this one is, okay, well, this one is 401, this one is 402. Doesn't matter. It's not a coincidence. All right. Now, part C says twice. Again, everything stayed the same. N is says 5, P is still 0.167, and QI is still 0.833. The only thing that changes 2, because it says a 3 appeared twice. Okay? Appeared twice. So you can see plug it in. 5 combination 2, 5. Okay. PRB combination 2 equals 10. Then times in parentheses, okay, 0.167 raised to the power 2. Okay, close it. Times 0.833 raised to the power 5 minus 2. 5 minus 2 is 3. Okay, that'll give me 0.161. That's right there. Okay, that's it. Very easy. So following the same process, you can get 3 times and 4 times, and I have it here for you. Same process, just the only thing that changes is the x. So when it says 3 times, if 3 appears 3 times, that means our x is 3. We plug it in here, right here, x is 3. Every other thing stays the same. So we have, okay, 5, okay, PRB, you go to NCR, combination 3, equal, then times 0.167 to the power 3, 0.167, okay, raised to the power 3, close this, times 0.833, 833, okay, raised to the power 5 minus 3 is 2. That gives us 0.032. You can see right here we are 32. This is just rounding error. Otherwise, it's still the same thing. 0.032 or 0.033 is the same. So when S is 4, when it says 3 appeared 4 times, just put x4 and repeat the same process. I leave that one out for you as a practice for you. You can practice that one, okay? So this is basically what is binomial probabilities. This is how to calculate it. One more thing I want to touch before we conclude the lecture is this, that sometimes people ask, how do we know when to use binomial? Having explained the properties of a binomial experiment at the beginning of the lecture today, but sometimes if you see a question, you might not know what to use it, whether to use binomial or not. So in that case, I give this example. Look at these examples here. It says, this scenario says, let us assume that we need to select 12 jurors from a population that is 80% Mexican American. And we want to find the probability that among 12 randomly selected jurors, exactly 7 are Mexican Americans. Does this procedure result in binomial distribution? If the procedure results in binomial, identify the values for n, x, p, and q. Part C says, use the binomial probability formula to find the probability of getting exactly 7 Mexican Americans when 12 jurors are randomly selected from the population that is 80% Mexican American. So let's start from part A. It says, does this procedure result in binomial? Well, let's see. First of all, the outcome will be 2. Either they are Mexican American or they are not. See? So that gives you binomial. Also, the probability is constant, 80%, which is 0.8. These 2 outcomes actually, and also there's fixed number of trial, 12 of them, 12 jurors to be selected. So N and P are fixed, constant. And also there will be 2 outcomes. Either they are Mexican Americans or they are not Mexican Americans. So that answer is yes. Yes, because if the jurors are either Mexican Americans or they are not. That's number one. Number two, the number of trials is fixed, 12 trials. See? That means 12 jurors will be selected. That's what we call it a trial. Then the probability of 80%, which is 0.8, remains the same for each juror. So yes, the answer is that it is a binomial. Okay? So you can see why it's a binomial. Again, let me repeat. There are two outcomes. Either they are Mexican American or they are not. Two, the number of trials is fixed, 12 trials, because 12 jurors will be selected. Three, the probability of success is 80%, which is 0.8, and this remains the same. That makes it a binomial. That's how you know that this question is a binomial probability problem. Okay? Number two says, if the procedure results in binomial distribution, identify n, x, p, q. Okay. N, 12 jurors. Okay? That's right there. 12 jurors. Let's find out p. It's a population that is 80% Mexican American. That means p is 80%. That means 0.8. Q is always 1 minus p. 1 minus p is 0.2. So we have identified n, p, and x. X says exactly 7. Exactly 7. So our x is 7. So once we have it, let's find this probability. Say, find the probability, use the formula to find the probability of getting exactly 7 Mexican Americans. Remember the formula here? We have it here if you still remember. NCX times p to the power x times q to the power n minus x. Okay? So let's go there. Anywhere you see n, put 12. Anywhere you see p, put 0.8. You see x, put 7. And q, do 1 minus p. I'll give you that. Okay? 0.2. So we plug it into the formula right here. So we have it as, okay, probability of getting exactly 7 is 12 combination 7. So we got 12. Press PRB. Go to combination 7. Press the enter key, then put 7. Okay. Press the enter key again. It's 792. You can see right here. Okay. Times, in parentheses, 0.8 to the power 7. 0.8 raised to the power 7. Okay. Which is then times 0.2 raised to the power, have 12 minus 7. 12 minus 7 is 5, right? I think. So it's 5. And okay, close it and press the enter key. 0.053. You can write that. 0.053. Okay? So this is what we call binomial probability. Okay? And now, before I conclude the lecture, let me state here that in the subsequent lectures, we do more examples on binomial probability. I'm going to show you how to use a table of binomial probabilities to calculate this, so that you don't have to go through the formula all the time. Binomial probability table basically gives you the probability. All you have to do is to add or subtract, as the case may be. I hope you enjoy my lecture. Thank you so much for listening, and I will see you in my next lecture. Okay, bye-bye.